Hopefully everyone can see that. And I didn't know I was following that amazing cast of speakers. Geez, that's a tall order. Um, I have to follow Robin Cotting and Brian Ponce. I'll try my best. So, welcome everyone to Efficient Class-Wide Math Intervention. I'm Ben Solomon. And if we haven't met before, I'm a professor at the University at Albany, State University of New York. I'm a school psychologist myself. I got my PhD at UMass Amherst a long time ago. And I study math assessment and math intervention. Those are my primary areas. I also do some work in research method and statistics, but assessment and intervention has always been my area. Um, I actually do work with a number of speakers that are panelists at the patent conference. I work very closely with Dr. Brian Ponce. I do work with Robin Cotting. I work with Dr. Amanda Vanderheyden. I notice my good Canadian friend Dr. Anastaki, is also presenting at patent, and we all work pretty closely together to advance crucial topics in math assessment and intervention and try to provide strong advocacy on your behalf. So, and yeah, so that's me. Let's get started. So our agenda for today in the brief time we have, first I'm going to rationalize class-wide intervention. I'm going to explain what it is and why we do it, because it's sort of a funny term. Sounds sort of like an oxymoron. How can intervention be class-wide, right? Isn't it supposed to be individualized? I'm going to review how we determine whether class-wide intervention is necessary based on data from your students. Specifically, I really emphasize the use of a very specific form of fluency assessment that is used within Brian Ponce's program, Amanda Vanderheyden's program. I'm sure you've heard converging messages across speakers on the importance of fluency data. I'm then going to talk about how to design class-wide intervention, starting with sort of a base level of explicit timing and moving your way up. And then we're going to go into how to progress monitor based on class-wide data, because that requires a slight adjustment because it's not individual students. It's also math data. Many of us are far more familiar with progress monitoring with, for example, oral reading fluency. And then I'm going to do a quick wrap up, and then I'll open it up for questions. All right, here we go. So what is class-wide intervention? And again, is intervention for an individual student? How can an intervention be class-wide? So first, let's consider a definition of intervention that I very much like. Intervention is the strategic and selective intensification of core features of instruction for an individual or group of students beyond that which is typically delivered to all. Okay, and you'll see the bolded words there are strategic and selective. Keep that definition in mind as we go to the next slide. So that definition suggests intervention is applied based on observed performance. That is, it is selective, right? Intervention isn't something we use for all students necessarily. We employ it when data dictates it must be used. So that's one of the key distinctions there. And intervention is intensified instruction. That is, we strategically, and I always use this sort of analogy to dials. People seem to like that. And I also often think of Spinal Tap, for those familiar with the 80s parody, where they dial it up to 11. So when we dial up class-wide, when we dial up our core curriculum, right, we're not dialing up the whole thing. We're identifying key areas of instruction, right, in terms of how we present the data, the way we practice the skills. We pull those out and we turn up the dial on those areas to accelerate the learning rate. And that makes it strategic, right? I think sometimes this gets lost in the mix, so to speak, because there's so many different intervention programs out there. and we tend to get very excited. And so we want to grab different programs or we found a new program at the National Association for School Psychologists Conference, and we want to bring it to our school, right? And we forget that an intervention has to align with our curriculum and has to very strategically dial up elements of that curriculum. So even if it's a good program in another context, it can be an inappropriate program within our context if it doesn't align well and doesn't ramp up the skills our students are currently learning. So there is the selective and strategic elements that define intervention. There's also no strict requirement that interventions be applied to a certain number of students. Again, we tend to think intervention, we tend to think, okay, one, two, three, four, small groups of students. But a lot of the research shows there's no group size requirement in terms of what makes for intervention. It tends to work equally well, so long as we keep our students interested and engaged. So with that said, um, we can absolutely have class-wide intervention because it fits that definition. And we further distinguish class-wide intervention from tier one, again, by the intensity of the procedure. It needs to be more intensive than whatever we're doing in tier one. It needs to involve some level of resources beyond what we use in tier one. And again, it has to align very nicely onto our curriculum. It has to advance our learning goals. Research has shown if the intervention is sort of detached from the core curriculum, it's not going to help much. And that's fairly that's fairly predictable. Intervention also has to entail progress monitoring, and I'll discuss how to do that in a class-wide format. When we apply intervention at the class-wide level, one easy way to sort of make it clear it's not tier one, but it's also not small group tier two, is to call it tier 1.5. I actually stole this term from my friend Amanda Vanderhayden. Um, she uses it very often as she situates her programs, Spring Math, which I'll go into a little bit. She calls it a tier 1.5 program, and I really like that term. I think it sort of helps explain where this intervention fits in. She also makes a really good point in some of her more seminal articles. She points out that if in tier one, if we have many, many, many students who are not responding, there's no way to know who actually is appropriate for tier two because our base rate is super high. So if 60 or 70% of our students aren't responding to tier one, there's no way to make an instructional decision as to who should go to tier two. Our measures aren't tuned to handle that base rate. And so we apply tier 1.5 so we can bring our base rate of non-responsiveness way down. And that's where our instruments are tuned. And that allows us to make valid decisions as to should go into tier two. As we make these decisions, we use fluency data. Okay, we many school psychologists here, so I'm sure you're very familiar with that, but I can't emphasize it enough. When we make decisions about whether tier 1.5 is needed, when we make decisions about what skill to move in a class-wide format, it really should be fluency data. What is fluency data? So Carl Binder, a seminal researcher in the precision instruction field, he wrote a key article in '96 where he operationally defined fluency as accuracy plus speed. Okay, and that has shown to be not just convenient or easy to understand or operationalize or observe. Fluency data has been shown to be one of the most outstanding predictors of students' retention and generalization of behaviors, right? Whether they be math behaviors, reading behaviors, social skill behaviors, bike riding behaviors, whatever it is, okay? If we can define fluency for a given skill and fit it within that accuracy plus speed context, and then measure students to a indicated benchmark, to a threshold, that is one of the best predictors that they will be able to use that skill in the future and remember it. Okay, and that's especially important for math because math skills tend to be practiced in math class. Unlike reading, students don't get a lot of opportunities unless they seek them out, I guess, to practice their math skills outside of school. So it's really important they have really high fluency in that classroom because, again, it's the only place they may get a lot of practice in it. Okay. So what are some examples of fluency data? On the right, you actually see a fluency sheet. That is a real fluency sheet from a study. It's actually a study I'm in the process of conducting with Amanda Vanderheyden. We finished part one in the spring. We're about to do part two next spring. Super excited. But we did class-wide intervention on 5 third-grade classrooms, and we progress monitored the students daily using math curriculum-based measurement and tracking their problems correct within a minute's time, which is a type of fluency data, widely accepted type of fluency data. Amanda and I actually validated the use of these kinds of measures in a study we conducted a few years ago. So, and obviously we weren't the only ones either. So you can see an example where on the right, um, this is actually scored, I think this is digits correct per minute scored on the right, but just a very simple example. These are not complicated instruments. They focus on a single skill and they have to be explicitly timed. And we have some good benchmarks I'm going to show you later as to what indicates mastery. Some other examples are on the left: number identification, simple addition or division, your basic operations, right? But in spring math, I think Amanda Vanderheyden has also creatively operationalized some more advanced math skills that go pretty much through 8th grade. For example, like least common denominator. She has a curriculum-based measurement for that, which I think is super cool. So the point is it needs to be brief, timed, focused on a single skill, and with a directly observable, calculable sort of performance number. So non-examples of fluency. And this actually is, these are quotes that my friend Anna Stocky and I found, and that we presented a few weeks ago when we were trying to distinguish a behavioral definition of fluency versus a non-behavioral definition of fluency, or what we might say is a evidence-based definition of fluency versus a non-evidence-based definition of fluency. So 3 quotes. Knowing how a number can be composed and decomposed, and using that information to be flexible and efficient with solving problems. All right, so this is a very generalized definition. Maybe we can create a measure of fluency if we have a specific skill on how numbers can be composed or decomposed, but then we get into flexibility. And that's not very observable. I don't know how really to operationalize flexibility per se. And so that makes this a non-proper definition of fluency. Also coming from my home state, New York Next Generation Standards, which I use as a poster child for a number of things. Fluency involves a mixture of just knowing some answers from patterns, and knowing some answers from the use of strategies. And actually, if you're in the Next Generation Standards and you look one bullet below, it says this: fluency means students are fast, accurate, okay, I'm with you there, flexible, and have an understanding they use strategies efficiently. A lot of skills loaded into that one sentence. Um, in both those cases, fluency has been redefined and would be very, very difficult to operationalize and measure in terms of knowing some answers from patterns and knowing some answers from the use of strategies. I don't really know how to set a threshold for that. I'm also not clear why that's useful for students. And and also if we go into the difference between fast, accurate, and then flexible, and having an understanding, again, which isn't observable. So I'm not going to dwell on these, but I just want to point out there is one scientific definition of fluency: accuracy plus speed, and that's what we use to make decisions. Okay, so I also want to further delineate a couple different kinds of math curriculum-based measurement. So when we talk about single skill um, math curriculum-based measurements, and I don't like that term single skill. It was actually Amanda Vanderheyden who corrected me once, and she had a very good point. I prefer to call them mastery measures because even single skills can sometimes involve sort of other prerequisite skills that have been learned in, for example, like division or least common denominator. So they're not single skills per se. They involve more than one skill, but they involve sort of one observable goal. So we call them mastery measures. So when you talk about math CBM and specifically mastery measures, okay, I do want to like to distinguish those from mixed skill probes that you do sometimes see with curriculum-based measurement that vendors, right? For example, you may see a vendor and they offer a screening. It looks like a CBM. It's timed for a couple minutes. It uses problems correct or maybe digits correct, but it has subtraction problems on it and addition problems on it. And maybe it's sort of getting into multiplication problems, and maybe there's different kinds of subtraction problems. Maybe there's 2 by 1 problems, maybe there's 2 by 2 problems, maybe there's 1 by 1 problems on there. We have concerns with those kinds of measures because it becomes very difficult to understand what skills students know and what they don't know. It all gets sort of averaged in the mix. So if you look at, for example, Spring Math or Brian Ponce's Mind, his program, um, they always involve individualized mastery measures, which I think is best. I'm also aware of computer adaptive screeners. Some may be good, some may be bad. There's some good information. For example, National Center for Intensive Intervention rates those things. But very few of the computer adaptive screeners, frankly, I don't know how they would do it, actually focus on mastery measure math probes because they're computer adaptive, right? So you really need a paper and pencil test there to do that correctly. And that also generates the critical benchmark data we need, whereas with the computer adaptives, you tend to get percentiles and standardized scores or vertically scaled scores, which is a whole nother beast. And they don't very clearly articulate what students know or don't know. You need a lot of context. So they can be useful in other areas. I'm not saying don't use them, and I know many schools do use them, but if you're thinking about evaluating for class-wide intervention, um, math mastery, curriculum-based measurement is best. Okay, so what skills, how do we determine whether class-wide intervention is necessary? How do we do that? So first, you need to decide your vendor, right? And you need to have a close look at your curriculum and make sure you know what skills are being asked of that curriculum. And based on the vendor you've chosen for your class-wide math intervention program, they're going to use different measures and different benchmarks. Although, frankly, the benchmarks are very similar because they all go back to a singular document, Dino and Merck in 1977. So you want to thoughtfully pick out your vendor. You want to, align that with your curriculum, and then you want to engage in sort of an initial screening to determine whether the intervention is necessary. So, for example, with both Mind and Spring Math, you'll find that they offer actually Spring Math does. There are recommendations for screening in Mind, but it's not, I don't think, necessarily specified as triannually, like in standard CBM. But in Spring Math, they offer triannual screening packages K through 8. So you take their screening package and you administer it, and it tells you whether the significance of the issue and whether you really should be employing the program. But you can use this with any curriculum-based measure. It's just really important you pick measures that align with your curriculum. What we often find is that when we have math problems sort of, in later grades, it almost always ties back to basic operations. I have never been in a school yet where teachers or principals aren't discussing concerns with math, and you do a class-wide screening, you find that most students, for example, are disfluent with multiplication. Anastaki makes the observation that multiplication probably is the sort of the big ticket skill. She suspects one of the most predictive skills in terms of students' ability to later access algebra, because that's it's just such a cornerstone skill, is knowing your multiplication table and being able to recall it freely. For example, when you later engage in again getting into sort of basic solving for X kind of pre-algebra problems. So as an example here, Mrs. Smith is worried about the math performance of her third grade students. They are struggling on the curriculum, which is currently focused on multiplication word problems. She administers a class-wide screener, which confirms the students lack fluent one-by-one multiplication fact recall, thus would not be able to easily complete word problems. But she also works back, checking on foundational subtraction and addition skills. So in this situation, class mastery is acceptable for multi-digit addition skills, but not multi-digit subtraction with borrowing. Develops a plan, begin with multi-digit subtraction and shore up that skill, move to multiplication basic facts to fluency, and then monitor. So the point here is that when you're doing that initial screening with math mastery measures, is that you should identify what are the skills in the curriculum that the students are currently learning. And if they come up as a class sort of deficient in that skill, don't stop there. Do your classic survey level assessment, work backwards until you find the earliest skill that they are deficient in as a class and work from there. Because as Anastaki says, math is relentlessly hierarchical. You can't skip rungs of a ladder. So even many of you have probably learned how to engage in SLA with the individual student. The same logic applies at the class-wide level. In terms of determining whether your class is at risk, that's sort of a funny thing, right? Because it's not a singular being. um, there's some adaptations that people have done. I do like Amanda's. She uses a median mastery rule. So what she states is based on the benchmark her program provides, she says at least 50% of the students should exceed that benchmark. And if 50% of the students exceed that benchmark, then your base rate is, it's still a little elevated, but at least it's sort of in a functional area and you're probably doing okay. But if more than 50%, if 50% or more of students are not achieving fluency on grade level math skills, now this is when class-wide intervention is called for. And that's when we need to begin to progress monitor and we begin to need to think about what we're going to do about that. Unfortunately, because our curriculums in America are pretty mediocre, and because our state standards, are also generally speaking sort of ineffective, you'll find that most students are just fluent, especially in basic operations, because they were never given the ability to practice those operations within their curriculum. And then we can develop a problem statement, just like we do for an individual student. So for example, 70% of students were identified as below fluency on the fall screening of subtraction from 18, with an average fluency score of 10 problems correct per minute. Target performance at this screening period is 20 digits correct per minute. So we develop a problem statement just like we would do for an individual student, right? How are they performing? And, relative to what is the socially sort of constructed goal for them. We just adapt it for the class-wide level. And we actually, I'm writing up a study right now, a student's dissertation, where we're actually exploring whether this class-wide um, framework, this class-wide problem solving is reliable and valid. And what we've actually found in a really cool statistical simulation is that it's incredibly reliable and valid, which I guess makes sense because the precision of math CBM is very high to begin with. So when you elevate it to the class-wide level and average across students, but we have found this class-wide decision making works very well and is very efficient and very accurate. I keep referencing thresholds, and you may be thinking, where on earth are you getting those? What are these thresholds you speak of? So the thresholds for math fluency, it's sort of neat, right? Because they all trace back to a singular document, and we have found the thresholds actually are fairly universal. That if we can create a accuracy plus speed directly observable test of a math skill, these thresholds tend to be valid. They're what Brian Ponce employs in his program for the most part, and I'll show you his thresholds in a second. And all of Amanda Vanderheyden's spring math benchmarks are actually adaptations of these thresholds. And so Dino and Merck in 1977, I don't know how they guessed it, but they were pretty spot on. They sort of theorized that in grades 1 through 3, on a given math scale, if students could identify between 0 and 9 digits correct per minute, that would be sort of frustrational level. That's a skill they're sort of at an acquisitional level. They need to work on. They need to learn explicitly. And sorry for the typo. 10 to 19 digits correct, not 919. That would be the flash. That would be burning the paper up with the pencil. Um, that's sort of an area where students really just need a lot of practice, that you can pull back a little bit on the explicit instruction and feedback. At that point, what they really need is structured practice. Okay, until they exceed that benchmark, now they're in a better zone, where you can sort of consider them to have mastery. The reason these are lower than the grade 4 benchmarks is because students at that age just don't have the fine motor skills yet to really write at a very fast pace. So they're given a little leeway. In grades 4 and up, 0 to 19 is considered sort of at an acquisitional level where students still need a lot of help. And then 20 to 39 is where students need a lot of very structured practice, which we'll get into. That's the whole point of this. And after that, they're considered mastery. So those are great rules of thumb for deciding whether a class needs class-wide intervention on a given skill. And they've remarkably been shown to hold up across skills and across time. These are similar benchmarks from Brian Ponce and Gary Duhon from the MIND program. They've outlined a number of thresholds that you can find for free on their website if you just Google Ponce Mind. And I know some of you went to his presentation this morning. They come right up. If you go to the Mind page, they're actually on the very bottom. They've outlined a number of benchmarks based on their research as well you can use to decide whether students are above or below sort of a mastery level and thus may require class-wide intervention if enough of these students within a given class are below the level. All right, so we've talked about what class-wide intervention is. We've talked about the importance of using fluency measures. We've talked about using fluency measures to determine whether class-wide intervention is necessary. Now let's get into design. Okay, so Um, in terms of designing class-wide intervention, I mentioned that there are certain vendors, right? We can use that make the job very easy. I mentioned Mind, I mentioned Spring Math. There are others, but those are the two I'm familiar with. And that, to be frank, I collaborate with their authors. So I'm just very familiar with those programs, but there certainly are others. I don't mean to provide an endorsement of any kind. Those programs make it easy because they do a lot of the hard work for you, right? I'll get into differences later in this lecture, but because a lot of thought has gone into the assessments, gone into the instructional routines, those aren't things you necessarily need to think of. The only thing you really need to consider is, do those vendors, as you select them, do they align with your curriculum such that you're teaching and reinforcing things that are actually instructional objectives? If you don't use one of those programs, though, you can still design your own class-wide intervention. Okay, and there's been tons of research on this, lots of different variations, looking at how we present things on the page, at what time do we do the practice, how long do we do the practice, who's facilitating, do we use individuals, do we do small groups, do we do feedback? There's there's been a ton of research on this, and we could speak for hours and hours about it. I boiled it down to three. I boiled it down to three elements you should be mindful of if you're designing your own class-wide intervention program or evaluating other programs, because these are elements every program should have. In my mind, not that I've done the meta-analysis, these are the three biggest bang for your buck components you can add to a class-wide program to increase the rate of learning for a given group of students on a singular math skill. So we're going to start with time practice. And in my belief, time practice is the absolute core. You can't have a tier 1.5 intervention, a class-wide intervention, if it doesn't involve time practice. And there's a reason for this, okay? If you look across common American, or Anna tells me Canadian as well, Canadian curriculums, they tend to move through topics very quickly. And they tend to focus a lot on solving addition problems in 97 different ways, right? Or very quickly moving to word problems before students have mastered addition and know computationally what to do. And so because of that emphasis, students have just a remarkable deficiency in practice opportunities when it comes to basic math skills. So maybe they've been taught sort of conceptually what addition is. Maybe they have a sense of that, although it's my belief you can't have a great sense of that until you are very fluent on addition. But because they've had no opportunity to practice it over and over and over and over and over again, okay, computationally, students in this country tend to be very weak, all right, unless they're very sort of gifted in math. And so they just require very few trials to get to mastery. Because of that landscape where students are given very little practice on skills, providing that practice is one of the absolute best things you can do for students. And this is really good news because it's a pretty easy problem to fix, right? There's really no secret to why students are doing poorly in math on average in this country. We know the reason, right? And lack of practice opportunities is the big, in my opinion, one of the biggest ones, if not the biggest one. So that's the good news. We know why. The second piece of really good news is that the practice opportunities actually don't need to be that long at all. If you can do between 2 and 4 minutes of daily practice with your students on math facts, I will, and you follow my advice, I'll put money on the table. You will see growth, okay, at a class-wide level. You'll still have non-responders. That's how RTI works. But at a class level, I promise you will see growth. So when we do time practice, you need to plan on about 2 to 4 minutes of what we call explicit timing. Okay. You can distribute this. So, for example, Greg Schutte, a professor at Oklahoma State who works with Brian Ponce, Brian Ponce, Gary Duhan, and I, we did a study a number of years ago where we split the time up, maybe 2 minutes in the morning, 2 minutes in the afternoon. I think we did actually we had one condition where we did 2 2 2 2 spread throughout the day. That works better. It's better to have a number of smaller sessions than it is to have one what we call massed practice session. But anything is better than nothing. So if you can only do one 4 minute session a day, that's still great. That will still be very helpful. It has to be daily. All right. The research shows very clearly that if you're going to do class-wide intervention, or if you're going to do intervention of any kind, really, it must be daily. When I work with my graduate students and we have situations where students aren't growing despite use of a good intervention, 9 out of 10 times I'll ask, are you implementing this daily? And they'll say, well, no, the student was absent. The teacher can't do it these days. 9 out of 10 times it's because it wasn't implemented daily. That is so key. The key element of time practice is opportunities to respond. Okay. It's simply structured time that's very important, time practice. And I think it's hard for some people to accept that because they think, how can that work? That sounds too easy, but it works. So in terms of resources for class-wide intervention, I've mentioned mine from Ponce. I've mentioned Spring Math from Vanderhayden. I've also linked, uh, and you can find the PDF of this on the patent website, on the patent conference website. I've also linked materials from a recent study I did with one of my graduate students, Lexi Payne. And we were actually running class-wide interventions. This is about 3 4 years ago. Um, it was actually more. Geez, it was right before COVID because we had a second phase of the study and we got cut off because we had to leave the school because COVID was just coming in. I'll never forget actually that when the principal came in and said, I think there's a pandemic occurring. I don't know. I don't think we can continue the math intervention anymore. Hopefully, it's the last time that happens. So, we did a study a number of years ago where we ran class-wide interventions with multiplication with third graders, and we were experimenting to see if goal setting helped the intervention, and we were also experimenting to see if set size, the number of problems we put on the page, was influential. I put all those resources from that study, which I think are pretty were pretty well developed. Lexi was great at this. I've put them on the resources too, so you're welcome to access those. And as far as explicit timing goes, on the right, you see a very standard explicit timing worksheet. Notice it is virtually identical to, I think in this case it is identical to the math CBM sheet. They are effectively the same sheets because when you run a math CBM, you are effectively doing explicit timing. It is the exact same structure, just one is designated an intervention material and one is designated an assessment material, but they're functionally, if not often, completely equivalent. So let me go back to and just say, so the key is the major foundation of class-wide intervention is you have to do daily timed explicit timing. And again, linked to the skills that you have identified as weak based on your class-wide survey level assessment. So, and if you look on the bottom right here, this is a visualization of the study I mentioned a little while ago. This is an ongoing study I'm doing with Amanda where we're doing class-wide explicit timing and class-wide cover copy compare in a local school. And we finished our first phase. So we have this cool data, right? And so what you're looking at is how third graders responded to class-wide explicit timing given over what was it, 2 weeks, given over 2 weeks of time. Okay. And so what you're looking at here is we didn't progress monitor. Oh, we didn't progress monitor every day. We came in roughly every other day. And so you're looking at students' growth slopes over the 2 weeks of explicit timing. And these should go quick. Students should master, discrete math skills much faster than they master, for example, oral reading fluency. Because it's a far more narrow specified skill in terms of one by one addition, right? If students aren't moving through skills very quickly, something's wrong. So you can see here in the graph, each line is an individual student, okay? And they're color coded. Students in the blue started sort of at the instructional level. So they were sort of, at that sort of 19 digits correct per minute threshold, but they still needed to work up. Our red students were below that. And what we found, and was almost unbelievable, was the Dino and Merkin threshold fit exactly at exactly 20 digits correct per minute. Students above that benefited from explicit timing. Students below that did not benefit. And notice, even though there's a lot of students who didn't respond here to explicit timing, the vast majority of students in the class still grew. And I think that's really cool because these students weren't given any feedback at all. They just practiced their math facts, but we didn't teach them any math facts. So if you just have them practice their math facts without even having to provide feedback, you're going to see growth in the class. You are going to miss your weakest learners, okay? And you may need to ramp it up for those individual students or for the class. But a lot of students will benefit from that straight up. I think that's really neat because it's so little time, it's such amazing bang for your buck. But if you have students that are weaker or you're looking for a faster growth rate, and of course you are, right? But maybe you don't have the resources to do this, the next thing you can layer on is problem feedback. This is when you actually provide feedback to the problems that students have been answering. Okay. So for example, they do their explicit timing worksheet, they complete it, and you did that 2 to 4 minutes, but now you need to take up a little bit more time. Okay. And there's a couple ways to do this. The easiest way is, I think, for the teacher to have a completed worksheet or to complete them sort of, model as she's going along, put it on the projector, okay, on the smart board, and she starts answering the problems herself as she goes along, and all the students are following. Okay, students are in pairs and switch worksheets, and they follow along with the teacher, and every problem that their partner got wrong, they circle it. Okay, and they go through the worksheet. They give the paper back to their partner, and now the partner needs to find the circled problems, the ones they got wrong, and needs to write the correct problem right next to the incorrect one based on the model that the teacher has put on the board. That's a very efficient way to do that. That comes right from Spring Math. They do a very close variant of that. Okay, that's a very quick and easy way to provide problem feedback. Another way, which we did in one study, is after students did their explicit timing, we actually brought all the worksheets back home with us, graded them all, gave them back to the students, okay? And then they had to review each of the problems they got incorrect, and then copy it a second time, so we saw that they actually did review it. But that was pretty effortful. I wouldn't expect a teacher or school psychologist to do that. You got enough to do. So having the teacher model correct computations with partners, so that way they're unbiased, um, circling the answers, then flipping them and having the student write the correct problem next to the incorrect one they got wrong. That's a great way to provide problem feedback. It doesn't even need to be that many steps though. Gary Duhan, and Brian Ponce was on the study, so was I. We did a study a number of years ago on a computer. So it was basically a computerized version of explicit timing, where students were presented a math problem and had to answer it. Okay. And if they got the problem right, there was a check mark and it moved to the next problem. If they got the problem wrong, there was an X. It didn't give them the right answer. It just alerted them that they got the problem wrong, but it didn't give them the right answer. And then it moved to the next problem. If we gave them just this simple level of feedback, they grew substantially. All right, so this was a pre-post design test. This comes from Journal of Behavioral Education, and you can see their equivalent at Outset. Um, but we had one group that got no feedback, that just did a straight explicit timing intervention. They grew from about 20 DCPM, 20 digits per minute, to almost 35. They grew. And again, a very powerful strategy. But students that were alerted which answers they got wrong, but not given the right answer, grew at a much faster rate. Their average well exceeded our Dino and Merkin benchmarks. Okay, so it doesn't even need to be give them the right answer. It can just be alerting them at which problems they got wrong. That's a very powerful strategy, but it adds logistics and time. And your teachers understandably may not be willing to do that unless they have a lot of help and resources. So you have to make the decision about whether it's worth it. The last one I'm going to talk about is goal setting. Okay. And so if we're going to, my order of intervention operations, explicit timing on the bottom, that's our go-to strategy. Um, problem feedback, that is our next strategy. And the third one that you can add, if you have the time and resources to do it, which has been shown highly beneficial, is goal setting. And what you're looking at on the right here is actually resources from that study I mentioned a little while ago that I did with my student Lexi. We developed, no, not we, Lexi developed these goal setting sheets. And so what we did is, after students did explicit timing, after they did feedback, they had their own sheet. They kept it in a folder with all their materials actually in their desk. So we never had to redistribute materials every day. They just kept all their intervention materials in their packet, in their folder for the week. It was super easy. And what they would do after they had their problems correct is they would then fill in a little bubble, okay, as to where they were that day, based on their not based on their initial explicit timing before they got feedback. Okay, so it was just their like a cold read and repeated readings. It was their cold explicit timing, and they'd fill in a little bubble and they'd connect the lines. If they went up, they also circled an arrow on top. And this was actually Brian Ponce's idea. Because if the teacher's reviewing these goal setting sheets, he made a really good point that we want to make sure they were paying attention to the sheets and were considering the feedback. If they circled the wrong arrow, we would know they weren't considering the feedback, that they were just going through just filling out anything. Um, Virtually all students were engaged, though. I don't think we had a single issue. So we have students circle the up or down or equal. It's not a, looks like a minus sign. It means equivalent arrow to indicate whether them acknowledging they went up or down. And so here's an example of a student sheet, right? And you can see they have a few downs, but the pattern's pretty clear. They go up. And what we found in our study was that students that engaged in this goal setting exercise at the end of their intervention period did significantly better than our students that were going through explicit timing and um, and getting um, and getting feedback. All students did explicit timing and got feedback, but the students that got goal setting on top of it, and we split it 50-50, it was randomized by class, um, did better. They notched about an additional 10 digits correct per minute at the end of I think it was how many? It was I think about a 3 week intervention because it was highly motivating to them. They wanted to see themselves get better, and this is a simple beat your score kind of thing. So that got them going, and you could see the excitement, right? You could see them turning to their partner, and they go, "Look, I grew this week. Look, I went up 5 problems. Oh, I went up 3. I went up 7." Um, they, you know, to because so many students struggle with math, when you demonstrate to students that they can improve in their math skills, they love that. It may be one of the first times they've seen that. So we found that students, contrary to a lot of pseudoscience and sort of and pop, psych myths that students hate time tests or that they hate time to practice or it makes them nervous or anxious. In my experience, that's all nonsense. They tend to really like these activities because they're short, they're structured, and students can see themselves grow on them. And once they see that, they're off and running. I've done this with hundreds and hundreds of students in my day at this point. I literally just finished with another 100 of them, and I did a post test with another 100 just a few days ago. And I have yet to be in a situation where a student has had an anxiety attack. It has never happened. Not saying it can't, but it's never happened. So um, engaging these exercises, and especially with the goal setting, so they can literally have a visual representation of their growth, that tends to be very beneficial. So I mentioned earlier on that I was going to distinguish between mind and spring math for you because I keep calling them the vendors, right? Well, how do these vendors differ? And I've referenced them a lot. So again, if you're engaging in sort of class-wide math intervention, these are the two vendors that I'm most familiar with and are, in my opinion, most focused on what have been found to be the scientific sort of bases of class-wide math intervention. All right, there's other vendors, other programs, um, but these two, everything I've explained in terms of the scientific behavioral research on how you might formulate a class-wide intervention, these are the two that have really sort of embodied it, in my opinion, the strongest. And again, you don't need to use either of these vendors. I don't make any money off either vendors. Um, you can design your own program based on your school's curriculum and what skills they're working on, but these two programs are really good bang for your buck. And I just wanted to spend a minute to explain the difference between them. So Mind, from my colleague Brian Ponce and Gary colleagues and Gary Duhan, both at Oklahoma State University. Go Pokes. Their core is explicit timing. Okay, and now you know what that is. They also layer in cover, copy, compare for non-responders in small groups or individualized. I'm not going to get into cover, copy, compare now. I'm sure many of you know what that is. Um, we've been playing around with use of class-wide cover, copy, compare as well, um, but we're sort of still in the process of that. Explicit timing is the way to go. And in the Mind system, everything's sort of individualized to student. So the teacher decides sort of week by week which students are working on addition, which students are working on subtraction, but everyone engages in the explicit timing exercise at the same time. Okay. It's all free. You can go to the Mind website right now. I'm sure many of you have been to it, and it is very smartly thought out. The assessments, I know a lot of thought has gone into the assessments. They conform to everything I discussed about good mastery measure curriculum-based measurements. They've got good benchmarks. They have a well articulated scope and sequence across grades in terms of math skills, but it's all manualized. Okay, I mean it all needs to be printed and done yourself. All right, it's a free material, so there's no sort of technological support at all. You need to engage in all the printing. You need to give the assessments. You need to determine, which students are or are not below certain benchmarks. You need to organize with your teachers, get the probes printed, scored. There's no scoring software. Okay, you need to sort of set that up on Excel yourself, which frankly for most school psychologists is easy because we tend to be good with data management. But nevertheless, there's a lot of work that needs to go into maintaining the system with Mind. It also goes K through 4. With Spring Math, it's explicit timing, but it has a far more elaborate sort of class-wide routine. Whereas with Mind, it's really just explicit timing. With Spring Math, it's explicit timing plus then a paired cover copy compare where your high performers and low performers are matched and they engage in sort of a mutual cover copy compare with each other. Then it moves to class-wide feedback on the explicit timing. So that just like I said, the teacher sort of starts modeling the answers to certain to the questions, and students follow along. Then there's goal setting, okay, just like I discussed. Um, and there's a class-wide incentive system too. And there's also a complete structure for individualized interventions for students that are not responding to the class-wide intervention. As Amanda would say, Spring Math is not a tier 1.5 program. She'd kill me if she heard me say that. It's a math MTSS program, right? It's a complete framework from tier 1 through tier 3. It's just one of its signature sort of package, its signature practice is its tier 1.5 routine in there. Okay. Um, but it is a complete math MTSS that has all the resources available to do individualized interventions with students as well. It makes all the calculations for you. It tells you when to progress. It tells you which skills to progress on. So it's got a very sophisticated computer dashboard, and that a lot of time and resources have been invested in that dashboard. So it does all the decision making for you that you would have to do yourself within the Mind program, but it costs a little money. I think Spring Math, don't quote me, please, because I'm not familiar with the with the cost structure, but I think roughly it's about $8 a head, which is frankly still about half what some of the computer adaptive vendors charge just for their assessments, mind you. But there is a cost to it, whereas with Mind, it's free. And it also tells you when to, again, move at the class-wide level. So it'll say on the dashboard, hey, your class is ready for this skill, move now. Or it will say, this class is ready for this skill, but these students still need to be working on this skill. And you should be using these materials to engage in individualized or small group interventions with these students. It tells you all that stuff, it's really cool. I really enjoy, working with it, and I'm supporting its use in a couple of schools locally. It also goes K through 8. So I just wanted to differentiate those two programs and what they offer. And again, I know Amanda and Brian are speaking at Patton, which is super exciting. And I imagine a number of you have attended those webinars too, where they're presenting on their products. But those are the two go-to for Tier 1.5. So can't they do all this stuff on a Chromebook, right? In my opinion, no. There are certainly, I think, computer-based math programs that can be helpful, so long as they conform to the features of explicit timing that I have discussed. But what research has shown is students really need, the best practice is still paper and pencil, okay? And again, a lot of the computer programs you see that I'm not going to name, they tend to be gamified and cartoony. They don't have a lot of opportunities to respond. They sort of emphasize and this sounds like a good thing that they emphasize state standards and they layer onto the curriculum. Those are good things, but they also carry their flaws, such as a real big focus on conceptual understanding, multiple strategies, quote unquote, sort of tricking students or trying to make things more difficult because it's not focusing on basic operations and loading them up with time practice. They tend to be less effective if they have any effect at all, to be frank. So I think the best programs, and this is what mine and Spring Math do, is it's paper and pencil every day. And unfortunately, that's been found to be most effective. I know Brian is actually working on a computer program right now that sort of digitizes the explicit timing procedure, but keeps all the sort of the features of mind intact. So there are sort of similar programs coming out. So I'm not saying this is like a strict law or anything, but for generally speaking, the practice should be paper and pencil. All right, this sounds like Minute Math. Um, it is sort of, but it's not. Don't confuse, please don't confuse the two. Minute Math and worksheets are not well developed like they are in Spring Math or Mind, or as we did in that study I did with Lexi. There's no decision-making framework, no ability to intensify, no scripts for consistent implementation. With Minute Math, and I'm sure many of you have gone through it, you usually just get sort of a math worksheet told to work on a minute, and then you sort of go up a skill sequence as defined by the Minute Math people, but there's no real survey level assessment, there's no progress monitoring, so it's different. It's very different when I'm explaining. And I'm just going to hurry up a bit because I see I'm running a little bit short on time. Another thing I want to address is, mostly what I've been talking about is memorizing math facts and or procedures, right? We don't memorize the answers to 2 by 2 addition problems. That's useless. But we do memorize the procedure for solving it. However, we do need to memorize our multiplication table, multipliers, 0 through 12, or really 2 by 12 because 0 and 1 are just, procedural tricks. And we do need to memorize our 1 by 1 addition facts. We do need to memorize our subtraction facts from 18. Um, and there's a big debate in the field about how helpful memorization is. I make the argument memorization, and not just me. I'm actually one of the lots of people have made this argument before me. I'm just joining. I'm just joining the party late. Lots of people have made this argument. Memorization is really important. Okay, memorizing your basic facts is absolutely vital. So yes, I am encouraging a class-wide intervention that is designed to teach students sort of quick recall, quick memorization. Um, but what research has shown is that that memorization is super vital because you don't want to be thinking about your times table on your fingers when you're doing algebra. Okay, that's Anastaki's point. And she frankly has found that she can almost pick out who's going to fail or pass her calculus class based on who she sees counting in their head on multiplication when they enter the class. So um, the memorization is really important. So yes, I have emphasized a procedure that focuses on sort of memorization of math facts or procedures, but that was very intentional. All right. So evaluating class-wide intervention, I'm just going to try to go for or about an hour. So I'm just going to try to go for another 5 minutes. So we have 10 minutes to answer questions. Key feature of intervention is progress monitoring. Um, and to do this, progress monitoring with class-wide intervention just follows our screening routine. Okay. I recommend you progress monitor about once a week, which is what they do in the spring math routine. Okay. And again, in terms of whether the class is going to move skills, is based on whether the class median has exceeded the benchmark that you've specified, that you've drawn from your materials. And I think, again, in mind, it's individualized, but you can still look at it per week per student. But it follows the exact same routine as you would, in terms of progress monitoring as you would for an individual student. And you want to make sure you are doing it weekly, at least weekly, so that when your class masters a skill, you're not wasting any time. Okay, you're moving skills as quickly as possible because you have a lot of skills to cover, right? There can be 20 or 30 critical skills to master from the fall to summer, and you can't be spending a month on a given skill. You need to move quick. So the moment your class-wide median indicates that the vast majority of students have mastered a skill, you need to move on. Again, don't leave your students who haven't mastered the skill behind. They can go into small group intervention that's progress monitored more frequently, all right? Using the same materials. So you follow your MTSS framework, but you should progress monitor. And again, weekly seems to be the sweet spot for this. Okay, so I'm going to wrap up with in the last 3 minutes before questions with a little quiz. Some of these questions are ones Anna and I gave at a recent webinar, and we had fun with the answers. So normally I'd put this in a poll, but just the way this is structured, I'm just going to ask you to think about your response, okay? So what is the scientifically correct definition of fluency? Is it being accurate with the skill? Being able to compose and decompose numbers? Accuracy plus speed? Or knowing multiple ways to solve a problem? So I'm going to give you a second there. And if you didn't know, based on the slide earlier, the answer is C, right? Accuracy plus speed is our definition of fluency. I didn't make that up. It's not my preferred definition. Okay, it is the scientifically based definition of what fluency is. And that's really important because I showed you slides where people were redefining um, what fluency is. Okay, we want to make sure we keep that in our mind because that fluency is sort of the origin of effective intervention. And so if people start messing with that, it's going to also mess with the effects of our intervention. Okay, what is the foundational layer of class-wide intervention? Is it explicit instruction? Is it modeling with manipulatives? Teaching multiple strategies? Or explicit timing? I'll give you a second there. And the correct answer is D, of course, right? So explicit timing is the foundational layer of class-wide intervention. A little bit goes a long way. Explicit instruction is super important. In fact, explicit timing really embodies our lessons and values and features of explicit instruction. But that answer is a little bit vague. We can formulate explicit instruction in many, 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 many different ways, depending on what the student's needs are and sort of where they are sort of in terms of their skill mastery. That doesn't really tell us specifically what to do. So explicit timing is the better answer. Modeling with manipulatives. I had this debate just a few days ago with someone. Using manipulatives is great. We all love manipulatives, right? Our little counting blocks, whatever have you. But the problem with manipulatives is it takes a very long time to teach students how to use the manipulatives correctly. Okay. And again, they get very few practice opportunities when they're using them. It may be helpful to sort of model or help a student visualize what a skill's getting at, so classic, summation within addition, right? Or taking away and subtraction. That's great. I'm not saying burn them. But we tend to find teachers overemphasize the use of manipulatives. And it really drags down students' learning rate because the use of manipulatives really is a singular learning trial. It's only one opportunity to respond, and it's not even on, within the context of how they would need to use that skill with more advanced operations. Okay, so and we also find manipulatives are used. We find personally manipulatives are used way too often, and often, frankly, with very young students who really don't know what they're doing and have a hard time keeping everything organized. So definitely not the foundation, but a big debate in the field. And teaching multiple strategies, for example, teaching 3 or 4 different ways to sum two numbers together or subtract, also not a great idea because it can confuse students, especially in the beginning before they're fluent on a singular procedure. Get them fluent on a singular efficient procedure first. So that's definitely not an element of class-wide intervention. How should we measure response to class-wide intervention? Just because we're going low on time, I'm going to answer this right off. Problems, digits correct on a mastery measure. That's been shown to be the most effective, reliable, and predictive measure of whether students are really mastering skills and can generalize them to more higher order skills as we move into the pre-algebra, algebra, and calculus scope and sequence. So Conceptual understanding, a debate in the field, that's important. Students should really fundamentally understand what operations are doing, but that sort of comes in parallel with understanding procedures. You can't have conceptual understanding without being very good on your procedures. We've talked about multiple strategies, and I've talked about scaled scores and computer adaptive tests. Those are great tests. They have their purposes, but those scaled scores are really difficult to interpret in terms of what they mean for a given student and what you should teach. All right, lots of references. All right, a few minutes for questions.